Some things which seem obvious are actually difficult to define with words. Some examples are time, distance, and temperature. And I especially like to think about time because we all kind of know what time is, but efforts to come up with a definition for time in words often fall short. They fall into several categories. One category would be where you just use another word to define it, but then you have to define that word. And then you use another word to define that, and you have to define that word, and you sort of end up in sort of a circular logic. Other categories are insufficient because it could also describe something else. Anyway, it's a fun exercise in class to try to come up with some definitions of time and then see why they fall short. And in these situations where the thing itself becomes very difficult to define, physicists resort to what's called an operational definition, meaning I don't know for sure if we know what it is, but here's how we measure it. Okay? And so, time is defined on what is measured with a clock. Okay, and so now, instead of having to define time, all we need to do is agree on how we build a clock. So, for example, if you make a pendulum could be a useful clock, and if I have a pendulum in my office and you have a pendulum in your office, and we have calibrated our pendulums, and I say, oh, well, this event took 5 swings of the pendulum, and you can look at your pendulum and say, oh, okay, I know what 5 swings of the pendulum means. And so we have created a clock that we can agree on. Now, pendulum's not a great clock because if you take it to the moon, it swings with a different period. And so we have ultimately come up with a definition of the ideal clock being an atomic clock, a certain kind of atomic clock, and it's a certain number of vibrations of a molecule inside of an atomic clock. And that is the definition of a second, and so therefore time is defined as what's measured with a clock. Similarly, we could define distance as that thing that is measured with a ruler. And for a long time, a meter was literally defined as a particular bar of iron in France. And if you wanted to know for sure that your meter matched up with the official meter, you went to France and made sure it was the exact same length as the meter in France, and that was the definition of a meter. And so then we could all agree on how to measure distance. Now, a meter is defined as the distance that light travels in a particular amount of time. So once we've defined time, we can define distance based on how fast light moves. But again, it's just like we are defining a technique for measuring distance, and then we don't have to actually say what distance is. We can just say, oh, well, distance is what light travels during a specified amount of time, and we can measure it. So that's good enough. Well, temperature is the same way. Temperature is actually a difficult thing to measure. It's a measure of how hot or cold something is, but what do we mean by hot or cold? And so the argument goes that temperature is what we measure with a thermometer. And now all we need to do is come up with an agreed upon way of building a thermometer and an agreed upon scale for putting markings on that thermometer, and we can understand temperature. Okay, well, so those are things that are hard to define. Thermal energy is a little bit easier to define. Thermal energy is just a kind of energy. And in fact, now this is my definition. I didn't go look this up. This isn't official, but I think it's good enough. Thermal energy is the microscopic kinetic and potential energy of atoms and molecules and their bonds. So if we imagine a molecule as a pair of atoms connected by a spring, they can vibrate, they can rotate, and they can move. They can translate. And also, the spring itself has potential energy if it's stretched. And all of those things together, the kinetic and potential energy of the vibrating, rotating, translating, and stretching molecules and atoms, that is what we mean by thermal energy. And if an object has a lot of thermal energy, then those atoms that make up the molecule are going to be vibrating, rotating, translating a lot, and stretching a lot. And if they only have a little bit of thermal energy, then they're going to be vibrating less, rotating less, translating slower, and stretching less. And so that is sort of a not super technical definition, but a reasonable intuition for what's meant by thermal energy. So thermal equilibrium refers to a situation where I have two objects where it is possible for thermal energy to transfer from one object to the other, and yet the net flow of thermal energy is zero. So this thing has some thermal energy, the molecules are moving around. This thing has some thermal energy, the molecules are moving around. And when we put them together, neither one gains or loses any thermal energy. And if that happens, we say, okay, these two guys are in thermal equilibrium, which means they have the same temperature. They have the same temperature. And conversely, if thermal energy flows from one object to the other, we say that one object has a higher temperature than the other. So if they're not in thermal equilibrium, the direction that thermal energy moves tells us which object is at a higher temperature. The one at a higher temperature, the thermal energy moves from high temperature to low temperature. Okay, so we are building up sort of an understanding and definition of temperature. So how do we make a thermometer? Well, it turns out that there are physical properties of an object that can change based on temperature. Some of the most classic examples you guys are familiar with. If you have a thin tube with a little reservoir of liquid inside the tube, as the temperature of that liquid changes, its volume changes, and so it can fill more or less of the tube. And by the way, the rest of the tube is filled with a vacuum. So again, as the temperature of the liquid changes, the fluid will either rise or lower in the tube. And if I put some markings on the tube, then I can use that to define temperature. And be like, oh, okay, I'll put a 0 here and a 100 here, and now I've created a thermometer. And if I want it to be useful, then I guess I'll have to get my friends together and have them build the same thing and put the same markings on it. And then we can use this thermometer to measure the temperature of various objects. Another good way to make a thermometer would be to have a container filled with gas, an airtight container filled with a gas, and a pressure valve. Not a pressure valve, a pressure gauge on the vessel. So it turns out, if the temperature of the vessel goes up, the pressure inside the gas will go up, and so the needle on the gauge will move. If the temperature of the gas goes down, the pressure will go down, so the needle will move. And again, if I put some markings on this pressure gauge and put some numbers on it, I now have created a thermometer that can be used to measure the temperature of different objects. Finally, and less useful for making a thermometer, one of the other properties that changes with temperature is the length of an object. So if this object has a length L0 at some known temperature, its length can change if the temperature goes up or goes down, and the change in length is going to be equal to some coefficient which depends on the material times the original length of the object times the change in temperature of the object. And here, this change in temperature is going to be measured in degrees Celsius or degrees Kelvin. Actually, we don't say degrees Kelvin, we just say Kelvin. Degrees Fahrenheit, degrees Celsius, or Kelvin. Anyway, a change of 5 degrees Celsius is the same as a change of 5 degrees Kelvin, so this formula works in Kelvin or Celsius. And this is the only formula that we're going to be using from this video to solve problems, but the video here is also meant to give us some background information on what temperature is and how temperature works. So I guess I will bring this down here because that was sort of the end of the lecture, where this is the part that you really need to know to do your homework. It is also useful to know about some different temperature scales, and I think you guys already know these, but the 3 temperature scales that we should be familiar with are Kelvin, Celsius, and Fahrenheit. I don't even know how to spell Fahrenheit. Let's see, Fahrenheit is what I have written down. Hopefully that's right. So these are Fahrenheit is really only used in a few countries. If we didn't have this class in the United States, we would probably only talk about Kelvin and Celsius. But since we're in the United States, we also talk about Fahrenheit. There are 4 sort of interesting temperatures that I'll look at: absolute zero, the freezing temperature of water, human body temperature, and the boiling temperature of water. And in Celsius, the freezing temperature of water is 0 degrees, and the boiling temperature of water is 100 degrees, and that's how the Celsius scale was created. In the Kelvin scale, 0 Kelvin is absolute zero, and the size of 1 degree Kelvin is the same as the size of 1 degree Celsius. So now all we need to know is what the offset is. Freezing is 273.15 Kelvin, which means boiling has to be 373.15 Kelvin, which also means that absolute zero is negative 273.15 degrees Celsius. Okay, and then human body temperature is about 37 degrees Celsius, which is about 310 Kelvin. So then the last scale is the Fahrenheit scale, and you might know that 32 degrees Fahrenheit is freezing, and 212 degrees Fahrenheit is boiling, and 98.6 degrees Fahrenheit is normal human body temperature. And you probably don't have memorized that negative 459.67 degrees Fahrenheit is absolute zero. Okay, the two scales that we will actually make use of in a physics class are Kelvin and Celsius. And let me just talk really quickly about absolute zero. Absolute zero is just something we observe empirically. If we keep making this box colder and colder and colder and colder and colder and colder and colder, eventually the pressure gets to zero. And even if we try to make it colder, the pressure never becomes negative. So the lowest pressure we can get in a gas is 0 pascals. And the result then is that the lowest temperature we can get is 0 Kelvin, or negative 273.15 degrees Celsius. Likewise, while this volume will never go to zero, if you keep making it colder and colder and colder and colder, it does reach a lower limit where the volume doesn't get any smaller. And again, you can keep trying to lower the temperature, but the volume will not continue to go down. So again, we sort of empirically observe that there is a minimum temperature. There is an absolute zero below which the temperature can't get any lower. And this does make sense with our definition of thermal energy. At some point, you can no longer decrease the vibrations, rotations, translations, and stretch of these molecules. You have taken out all of the thermal energy you can take out. And once you've reached the point where you've taken out all of the thermal energy you can take out, you have reached absolute zero temperature. Okay, I will see you in the next video.